Okay, so we're doing general physics 1. And as I mentioned, everything builds upon itself. But one of the things that we really need to start with are some basics. So first of all, if I were to write down 365, 7, 27, I'm making sure I am recording. So, yep, 27, 12. These, as it stands, are just numbers. There's nothing in here that tells me what these mean. There's no context or anything. Now, most of you look at those numbers and go, wait, but I know some of those. One is there 12 months in a year. So I can put units on it. So you got those units. There are 365 days per year. So we know that that's in there. And then these are days per week. So we actually have units. So numbers in physics have units. And you're really going to need, and we're going to do things what we call unit analysis that really helps us out. All right. Now, this weird one here, 27, you may or may not know that. Might not be something that you're familiar with or you've had before, but this is a really valuable one because 27 meters per second is approximately 60 miles per hour. And we as Americans, or living here in the United States, we don't necessarily think in meters per second. We don't necessarily think in metric units. So we want to have some rules of thumb in order to help us out to make sure that we are doing the calculations correctly. So if you wanted to calculate the speed of a turtle crossing the road and you get something on the order of 100 meters per second, you need to start thinking to yourself, that's probably not right. That's not realistic. That's not right. One of the things that I like to do when I give problems on an exam or people in the back of the book is we like to give you real world type of examples. So if we were to say a horse is running at 10 meters per second, well, that's probably a reasonable number. If we were to say a horse is running at 300 meters per second, that's probably not a reasonable number because we need to generate what we call rules of thumb. And those rules of thumb really help us out. And that's where we get into this idea of estimates, because we call them back of the envelope calculations. We call them estimates. We do a lot of those as well. So let's start looking at our unit analysis first. We're going to be using metric units. So we have a unit of length, which is going to be a meter. In my English system, it's a foot. We have a unit of time, which are seconds. And in the English system, seconds are also there. We have our unit of mass, which is going to be kilograms. And we actually have a unit of mass in the English system. We just don't normally talk about it. We call it a slug. So this is length. This is time. This is mass. These are fundamental units, meaning we don't really break them down into other units. So these are our fundamental units. So we also talk about derived units. We have a couple of other fundamental units, and that's related to charge. And we'll see that when we get into physics 2, but that is another fundamental unit. So we have fundamental and derived units. Now, one of the most common derived units that we have that we're going to have to keep track of, trying to give myself some room here without moving my screens. They kept blinking this morning, so I don't want to move my screens too much. But a derived unit is made up of other units, and force is going to be a derived unit. Now, in the English system, force is pounds. And when we talk about pounds, that's the act of gravity on our mass. And in the SI system, this is newtons. And a newton, 1 newton is equal to 1 kilogram meter per second squared. And my pound is actually a slug foot per second squared. So that's why we call it a derived unit, because we're using a mix of units. So other common derived units that we would have would be like velocity or speed. And if we're doing it in our metric system, we're going to do it in meters per second. If we're doing it in the English system, we're doing feet per second. Acceleration would be another derived unit. And that is going to be in our meters per second squared, or our feet per second squared. Now, the reason we go through this is because we use unit analysis to really help us out and to verify if we've done our math correctly, if we've done our derivations correctly, or things like that. So you're going to have a homework problem. You actually have a couple of homework problems in chapter 1. And you're told, I've been given an equation. And that equation is mass, and I'm going to use M meaning mass. And I'm going to use L meaning length. And you're going to have mass length squared is equal to, and we're going to do a question mark. And we're going to say mass times velocity. Now, when we're doing algebra, we can only add like to like. So the units on this side are in kilograms meters squared. The units on this side are in kilograms meters per second. And those definitely are not equal. So this is called unit analysis. So we're going to look at our units to verify that we've set up our equations correctly. So you've got a couple of homework problems that are going to have these kinds of things. So don't sweat it so much about what it is. No, you don't have to know how to do that equation, but all you're doing in the homework assignment is verifying that the units make sense. So one of the equations we're going to use a lot is velocity squared is equal to initial velocity squared plus 2 times acceleration times a position. So that's a common equation that we're going to use. A couple things I want to point out. This is our notation. We're going to use subscripts to really help us out in verifying where things. So this will mean initial velocity. What is our starting velocity? You may see it as v sub I. That also is an initial velocity. Or you see it as v sub O, which also means initial velocity. And if you go to different textbooks, you're going to see different textbooks. we're going to use X to mean position. And V is going to be velocity. And A is going to be acceleration. Yeah, so far here, what we've got is we just have an equation. We don't know how we got that equation. We just have an equation. By next week, you'll know how we got that equation, but that's all right. But by this week, so what all we're doing is we're verifying that this equation is doable. So my velocity is meters squared seconds squared because I'm squaring my units. Okay, so this is actually meters per second squared. So those are the same. So I'm going to end up over here, and since this is initial velocity, we know that that's pretty okay. So that's going to be great. But what we don't know is this right here. So 2 does not have any units. So it's unitless. So we're just going to deal with that. But my acceleration is in meters per second squared, and I'm multiplying it by meters. So if I were to rewrite this, I'm going to end up with meters squared seconds squared plus 2 meters squared seconds squared. So this equation is correct because I can add these 2 similar sets of units. I don't have to worry about anything else. This equation is correct. And so if I were doing my homework problem and it was asking me, is this something that can be done from a unit analysis point of view? We're okay because our units on both sides of the equation match. This helps you with conversions, okay? This helps you with conversions. So we're going to do our conversion here. I'm going to go through, we want to know, I have 136 centimeters per second. And we want to convert that into inches per minute. Okay, we need a conversion factor. And hopefully most of you have done conversions before. So this is just kind of a refresher. Well, one of the conversion factors we know is 2.54 centimeters for every 1 inch. And we know there are 60 seconds for every minute. Now, our unit analysis will really, truly help us out in doing this conversion. So I'm going to do my 136 centimeters per second. We are going to have to do 1 over our 2.54 because this is centimeters per inch. And I need inches on top. And then we've got our minutes on the bottom. So I need to do 60 seconds per minute. And my units will cancel. My centimeters will cancel. I'm left with inches. My seconds will cancel. I'm left with minutes. So I'm going to end up in the correct units in inches per minute. So that gives me a really good feel there. So 136 times 60 divided by 2.54 gives me, now my calculator, I'm going to write it all out here, 321.2.598.425. Okay, that's what the calculator gives me. But remember, we have to deal with significant figures. In my chemistry class, I am very, very persnickety about significant figures. In physics, I am not as persnickety about it, but we still don't need to be writing out this entire number. Now remember, significant figures relate to accuracy and precision. Okay. This case, we only have 3 significant figures here. 1, 2, 3. So our answer, now this is an exact number and this is an exact number. So these are exact. So these are not going to control my significant figures. The number I started with controls my significant figures. So my answer, if I'm multiplying, my answer should be in the lowest number of significant figures. 1, 2, 3. So I really should report 3210 inches per minute. And that's what I'm going to put in the WebAssign. There will be some homework problems in WebAssign that you're going to have to pay particular attention to the number of significant figures. I do have some extra videos on significant figures, but most of you have taken other classes and have dealt with significant figures. So just let me know if you need those. But for physics, most of the time, we're just carrying it to 3, right? So you're not necessarily writing out this entire number. So I'm going to stop real quick and see if there are any questions so far. Again, feel free to use the chat, because that's a great way to ask questions, and you can type it in at exactly the time that you think about it, and that will really help you out. All right, so we've talked about unit analysis. We've talked about significant figures. We've talked about these ideas, giving our units with numbers. I did get a question, so hang on just a second. I try to have my recordings posted by the next day. So just so that people are aware, I try to have recordings posted by the next day. This one will probably get posted today, but if I'm traveling between campuses, it takes me just a little while to get it, and Zoom takes about 20 minutes or so before it's ready to be posted, and I have to download it and post it back up. So, all right. And I usually will make an announcement or send out an announcement to say the videos are posted, so you guys know when they hit, so you can watch it in your email. All right. So we talked about significant figures. We've talked about unit analysis. We've talked about looking at some of the formats of things. Now let's talk about estimates. And why on earth do we worry about estimates? Okay, so estimates are something that we have to do to help us figure out, are we in the right ballpark? So for example, if we say a football player, since football started this weekend, yay, and I watched the Iowa State, Kansas State game, yay, it was great. But if we say that a football player ran 5,000 yards during a football game, we know that's not right, okay? You know, we know that a running back might get 100 yards. Sometimes a running back might get 150 yards, and in a really rare case, a running back might get 200 yards. But to say that a running back got 500 or 5,000 yards in the first game of the season, we know that that number is just not right. We've screwed up somewhere, right? We totally have screwed up somewhere. So we need to have an idea of those estimates. And we use estimates all the time. We use it to figure out, all right, if I'm going on a trip and I want to have enough money to make sure I can pay cash for my meals, we know that if I go out and I know I'm going to eat at McDonald's, and I'm going to eat at McDonald's 3 times a day, and I'm going to be gone for 5 days. Let's see, That means I might want to have $9 a meal. 3 times 9 is 27. 27 times 5, just because can't do that number in my head. That's about $135. I probably want to make sure I have about $150 in my wallet to cover those meals. So I just ran through an estimate. So for you construction guys, you guys are doing estimates all the time, because there's another thing that we have to do is deal with exact versus nominal. Right? You have to worry about exact versus nominal. If I go out and buy a 2x4, it's not 2 inches by 4 inches. We call it a 2x4, but it isn't a 2x4. So we're doing estimates like how much material are we going to need? We're doing estimates at looking at those calculations. In Blackboard, you have a couple of examples of estimates. I've done the number of pineapples in a storage or in a container. So if you think about a truck on the road and they're filled with dull pineapples, and you want to know about how many pineapples is a truckload of pineapples. It's not going to be exact. The only way we're going to get an exact number is actually go in and count the pineapples, but I can get a good idea of the number of pineapples. Another one would be, I have the number of atoms in a teaspoon of water versus the number of teaspoons in the Atlantic Ocean. So that's another one that you'll see as an example in Blackboard if you want to work through it. You also see things like this, and we do these examples all the time. I've got a Erlenmeyer flask filled with gummies in here, okay? And my Erlenmeyer flask is got 500 milliliters, and I want to have an estimate of how many jelly beans are in here. I'm going to take the number or the volume of one of these jelly beans, okay, and divide it into the number here, and I'm going to come up with an estimated number of how many gummy bears are there. Well, I got to figure out what's millimeter, right? What's a milliliter? Well, and I got to look at one of those and say, all right, I've got maybe a cubic centimeter here, and I've got to make a guesstimate of the volume of each one of those gummies in order to figure out how many are in there. So let's do one. We'll say a pallet of books contains. So we got one pallet of books. And we're told that there's 144 books. And we've got a crew of workers filling up the books. And we're going to need 15 or 16 pallets. And we're told that one person can load one pallet every 5 minutes. Okay, so this is a semi-load of pallets. So we want to estimate the time. We want to estimate the time that it takes to load one semi with 5 people. All right. So basically, I don't care how many books I have. We know that a person can load a pallet every 5 minutes. And we know that there are 16 pallets. So our rate of loading is 16 pallets divided by 5 minutes. gives me pallets per minute. And if I do that, and I get like 3.2 pallets per minute, right? But I got 5 people. Okay, so that's one person is a pallet for every 5 minutes. That's person. So basically, if I were to do this, I got 3.2 pallets per minute is the rate that we're loading the truck. And I've got one person can do 5 pallets for 1 minute. And this gives me the number of people. We should be able to load that truck pretty quickly. I'm getting about 0.5 minute if we're loading those pallets. So that doesn't make any sense. Estimate the time that takes. We'll load one semi with 5 people. We get 5 pallet or 3.2 pallets per minute. Nope, that's right. We divide that by 5. Yep. Divide that by 5, and it'll take them 0.62 minutes. And you can see that there's more than one way to do it. So your homework assignment that you have is you've been given a 55-gallon drum. And we want to know the number of Major League Baseballs that can fit in the drum. So you got a 55-gallon drum. We want to know the number of Major League Baseballs. So there's some information that you're going to need. Is what is the volume of a Major League Baseball? You need the volume of a Major League Baseball. So you're going to have to look it up. And you'll need to reference. So when you turn in your assignment, it better include the reference for where you got your Major League Baseball. Then you need to describe how you came up with the answer. And then you need to give me the number. Now, I am not grading on whether your number is correct. I will tell you what number I have for it, but I'm not going to tell you, I'm not going to grade on whether or not the number is correct. You may get marked off if your number is unreasonable, okay? If you tell me there are only 5 baseballs in a 55-gallon drum, I'm going to question that. I'm going to question that number, and I'll question it. And if you tell me there are 10,000 baseballs in a 55-gallon drum, I'm going to question that because again, that's not a reasonable number. That's the only reason I would count off on the number. I'm looking for your reference. I'm looking at how you came up with the answer, and you're going to provide me with just a page, just a handwritten page as a PDF. So make sure you go in on the CAM scanner and get that PDF, okay, so that you can record it as a PDF, and you're going to upload the PDF. So again, this is one of those things that we do and we talk about in general physics, but the idea here is to give yourself a way to look at your answers when we start doing the calculations, that for physics items, that it makes sense. Okay, it's a way to check your answer. It's a way to say, do I understand the concepts here? Rather than just jumping into something else. So that's one of the things that you guys need to do. All right. I'm not gonna start anything else new. So I will hang out for questions.